voltage with the current. V equals IR. The applications are as thus. Applications are in electrical wiring, in our mobile phones, in televisions, circuits, household appliances, industrial system, etc., etc. Now to the subject of the day, which is the continuation of our laws. We now enters today's segment. With today's segment, we start with the Boyle's law. The Boyle's law has its propounder as Robert Boyle's, and the statement goes as thus: that at constant temperature, the pressure of a fixed mass of gas is inversely proportional to its volume. The pressure at constant temperature, the pressure of a fixed mass of gas is inversely proportional to its volume. There is no Boyle's law without the Charles law. That's what gives us what they call the gas law. So now I read as thus: that the Charles law, that at constant temperature, at constant pressure this time, earlier on we know that on Boyle's law part we have constant temperature, but this time at Charles law we have constant pressure. And I read as thus: that Charles law states that at constant pressure, the volume of a given mass of a gas is directly proportional to its absolute temperature. At constant temperature, the volume of a given mass of a gas is directly proportional to its absolute temperature. So V is directly proportional to T at constant temperature. So invariably, in gas law, the law goes as thus: that PV over T equals to constant. So PV over T gives us the constant. So where we can see that the Boyle's law is pressure that is directly inversely proportional to its volume, whereas on the Charles law we have so on the Charles law, at constant temperature, the volume of a given mass of a gas is directly proportional to its absolute temperature. Absolute temperature marked, quote and unquote, the absolute temperature has to do with Kelvin. The degree centigrade, Celsius at this time, does not affect this law. So that temperature is absolute temperature. That's to say, degrees Celsius added to 273 makes up our Kelvin. Applications to Boyle's law are in syringes. We have applications in syringes. We have application in bicycle pumps. We have applications in vehicle engines. We have applications in medical equipment. We have applications in scuba diving. In Charles law, we have the applications in helium balloons. We have the applications in helium balloons. We have the applications in hot air balloons. We have the applications in automobile tires. In helium balloons, the volume of the helium increases with its temperature. So the balloon will expand when the environment is warm, and the balloon shrinks when the environment is cold. So at a certain a defined temperature, it has to be a regulated temperature. So helium balloons has an application in Charles law, which is that the volume of the helium balloon will increase when the temperature is beyond its regulated threshold, and the balloon will deflate or shrinks when the temperature goes below the regulated threshold. Also, the same thing applies to the hot air balloons. Also, we know that in tires, when a automobile tire is heated, it expands. It expands, and if the temperature goes down, so also the pressure of the tire goes down. So I want to move to the next law. Next law, which is the Archimedes principle. The Archimedes principle is credited with its propounder, which is named as Archimedes. Archimedes principle is credited to its propounder called Archimedes. And the statement is this: a body immersed wholly or partially in a fluid experiences an upthrust which is equal to the weight of the fluid displaced. A body immersed wholly or partially in a fluid experiences an upthrust to the weight of the fluid displaced. These has applications in shipbuilding. It has application in submarines. It has applications in hydrometers. It has applications in life jackets. It has application in hot air balloons. All waterways transportation, both inland and oceanic transportations, these are where Archimedes principle have its applications. So I repeat again that Archimedes principle states that a body immersed wholly or partially experiences in a fluid experiences an upthrust that is equal to the weight of the fluid displaced. And the applications, like I said, are in shipbuilding, then submarines, then hydrometer, then life jackets, and hot air balloons. And generally, we can see them in all waterways transportation, both inland and oceanic waterway transportation. The next on these laws is the Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction, and its propounder is Michael Faraday. The propounder of law of electromagnetic induction is called Michael Faraday. The statement is as thus: an electromotive force is induced when there is a change in magnetic flux through a conductor. An electromotive force is induced whenever there is a change in magnetic flux through a conductor. I say again that an electromotive force is induced whenever there is a change in magnetic flux through a conductor. The applications are as thus. Applications are in electric generators. Applications are in electric generators. Applications are in transformers. Applications are in transformers. Applications are in dynamos. Applications are in dynamos. Applications are in hydroelectric stations like Kanji Dam, Shiroro Dam, and many more. We also have applications in renewable energy technologies. We have applications in renewable energy technologies. Yeah, I want to add a peculiar or a related principle to the Archimedes principle. Before you understand Archimedes principle, you must understand what is known as the real depth or the apparent depth. Apparent depth and real depth, they also have relationship with the pressure in fluid. So, and they have relationship with mainly or mostly the Archimedes principle. A real depth is the actual physical depth of an object that is immersed in a liquid, measured from the surface of the liquid straight down to the object. If you have a glass of water in front of you, try and put a pencil inside that glass of water. So the pencil will not float, but will experience what is known as apparent depth or real depth. It will not go straight down, but you can measure its real depth. Even before you put it inside, you know its real depth. But it will show you right inside that water that it has whether a smaller depth that is assumed inside that water, which is mostly different from the real depth which really enters that water. So the real depth is the actual physical depth of an object immersed in a liquid, measured from the surface of the liquid straight down to the object. While we have the apparent depth is the depth at which an object immersed in a liquid seems to be seen by an observer. When you look at it, the pencil you put inside the water, when you observe it, it will look to you from above the liquid surface. But due to the refraction of light and the surface of on the surface of the liquid, the object appears to be at a shallower depth than it is in the real sense. So that depth is called the apparent depth. And I'll repeat that the apparent depth is the depth at which an object immersed in a liquid seems to be seen by an observer looking from above the liquid surface. Due to the refraction of the light at the surface of the liquid, the object appears to be at a shallower depth than it is actually. So when you put your pencil inside that glass of water, it will seem as if it comes up. However, it comes up, but the depth at which it enters is not what you see. You see a shorter depth inside, whereas if you bring out that object, consider the wet surfaces on the body, then measure. You now see that the depth that enters that water is longer than the shallower one that you are trying to see. So why does this happen? It happens that when light rays travels from the denser medium, like liquid, to a rare medium, to a lighter medium, like here, they bend away from the normal refraction. So because the mediums are different. When an object is coming from the air is a different medium. When it enters the water is a different medium. So there is always a tendency that it bends away from the normal refraction. So because of the bending, the object appears closer to the surface. That's how it looks, as if the length or the depth of that object is reduced. Whereas in the real sense, the object assumed the real length when it goes down into the liquid. So there is a relationship, however, between the real depth and apparent depth. So real depth over apparent depth will give us what we call the mu. The real depth over apparent depth gives us what is a ratio, which is refractive index mu. So from which we can know, if given the refractive index mu, you can now relate your unknown with the known. If you know your refractive index and you know your real depth, you can know your apparent depth. If you know your real depth with your refractive index, you can know your apparent depth. And also, you can know your refractive index once you know your real depth and the apparent depth. Now let's have a quick recap. Once again, a quick recap of all that's been discussed so far. The laws in physics, their preponderance and applications in everyday life. The laws are: the first law is the Newton's first law of motion, which is also called the law of inertia. Newton's first law of motion is also called the law of inertia. The applications are in seatbelts, automobile brakes, dusting carpets and rugs, packaging fragile materials, vehicle safety engineering, and lots of it in sporting activities. Also, when you're moving a bus, when a moving bus stops suddenly, so passenger tends to feel the movement forward because the body assumed the movement of the automobile already. So we have the second law, which is the Newton's second law of motion, also propounded or proposed by Isaac Newton. So it's that the rate of change of momentum of an object is directly proportional to the force applied, and occurs, that force occurs in the rate of change of momentum occurs in the direction of that force. So mathematically, we have the force as being equal to mass times acceleration. So the larger the force, the greater the acceleration, because they are directly related. When you had direct relationship, directly proportional, that is, they vary at the same time. When the force increases, the acceleration increases. If the force increases, the mass increases, and vice versa. Applications are also in rocket propulsion, vehicle manufacturing, sports, construction equipment, industrial machinery, etc., etc. You can have a quick illustration through an empty barrel, which will be easier to carry. But the more you have weights of concrete blocks and heavy objects inside a wheelbarrow, it becomes heavier, and you need more force to carry it. So we have on the third one, a recap on the third one is that we have another law which is called the Newton's third law of motion, which is credited to Isaac Newton. So for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Applications are widely seen in walking and running, swimming, rocket launches, ball flights, recoil of firearms, etc. So also, we can experience this law, the application of this law, when you see a swimmer enters the water as he pushes water backward, and the water pushes the swimmer forward. As the swimmer pushes the water backward, the water itself pushes the swimmer forward. So let's have the studio lines open for our callers. The studio lines is 070-4700-3969, 070-4700-3969, 070-4700-2969, 070-4700-2969. Also, we have the law of universal gravitation, which is also credited to Isaac Newton. Callers, you can call on 070-4700-3969. Hello.
Good morning.
Good morning. What's the name and where are you calling from?
My name is Tabayomide.
Mustafa Yomide.
Yes, sir.
From where? Your school?
Ikire.
Ikire. Mustafa Yomide from Ikire. Okay. From Fatima College, Ikire?
Yes.
What class are you again?
Sir.
SS1. Okay. So, how many laws are credited to Newton?
Sir?
How many laws are credited to Newton? To Isaac Newton. 3 laws. Okay. Tell me the one. Tell me one by one. The first law is what?
Initial laws.
Okay. Second one.
Wait, hold on.
Okay.
I want to recall.
Okay. You're trying to read this through somewhere? That's okay. Too bad. You're trying to have a cheat sheet. Okay. No. Hello? Hello? Somebody there? What's the name and where are you calling from? Too bad. So, hello? Okay. Now we have the law of gravitation, universal gravitation, also credited to Isaac Newton, making the 4th law credited to Isaac Newton. So the applications are in artificial satellites, space exploration, ocean tides, planetary motion, weather forecasting, everyday example, fruit falling from trees, rain falling to the earth, human beings remaining firmly on the ground. So we have the Ohm's law too, which is also credited to his propounder, Judge Simon Ohm. The applications are in electrical wiring. Mobile phones, telecommunications, TV circuits, household appliances, industrial electrical systems. Now we have also the Bohr's law. No Bohr's without the Charles. The Bohr's law and the Charles law, which is credited to Bohr's, Robert Bohr's, and Charles. So the applications to the Bohr's law is in syringes, bicycle pumps, vehicle engines, medical equipment, scuba diving. We have the Charles law too, which has its application in helium balloons, the hot air balloons, and automobile tires. So in the application of helium balloons, we know that the volume of the helium will increase with temperature, so that the balloon will expand in a warm environment, and the balloon will deflate or shrinks in a cold environment. So we also have the Faraday's law of electromagnetic induction. Which is credited to its propounder, Michael Faraday, which is a simple statement that an electromotive force is induced whenever there is a change in magnetic flux through a conductor. These applications are in electric generators. Hello?
Hello?
Hello, I'm here again.
I am from Partner College.
Yeah, I can say. So, you are telling me the Isaac Newton laws. Yeah, you told me the first one is law of inertia. Hello?
Hello, sir.
Yeah, state the laws of Isaac Newton. Or mention the laws of Isaac Newton. Hello?
Hello, I didn't know what to say.
Mention the laws of Isaac Newton. The first one, you said it's the law of inertia. What is the second one? Hello?
Hello?
You said the first law of Isaac Newton is the law of inertia, which is the law of motion. What is the second one?
Second law of electrolysis.
No. Newton's second law of motion. What is it? Hello? Now, before we round up, I want to give our listeners, mostly students, I want to give them a takeaway. These are questions that must be, you should be able to state the Newton's third law of motion and give two practical examples. The 3 is that why can a heavy ship float on water despite its enormous weight? Why can a heavy ship float on a water despite its enormous weight? Mention 3 applications of Ohm's law. Explain Boyle's law using a bicycle pump. Which law explains how electricity is generated in power stations? Mention any law in physics that you can observe in everyday activities and explain why. So before I close this program,
Hello, sir.
hello.
It is Mustafa Yomide, sir.
Mustafa Yomide, okay?
Yes, sir.
Okay.
Newton's second law states that
Okay.
the time rate of change of momentum
Okay.
of a body is proportional to the applied force and take place in direction of the force.
Thank you very much. God bless you. I've said it once again. Hello. Okay. Thank you. Your gift is ready, as you are one of our regular callers. So your gift is ready. The station will call you shortly to come over and receive your gifts. So before I close my program today, as we conclude the school on here, I remember, and I will always tell us to remember, that physics is not merely a classroom subject. It is a science of everyday living. So the laws of physics reveal that nature operates with order, consistency, and purpose. That teaches that understanding principles enable us to explain our world, solve problems, and create innovations that improve human lives. On behalf of the management of the Oxygen FM 96.9, led by its distinguished head of station, Mrs. Tokumbo Ishola, and the entire production crew and technical crew, we sincerely appreciate your time and participation. To all our listeners at home, special appreciation once again to the producer of this program, Mr. Femi Timothy Ogunyejo, for conceptualizing and producing these educational broadcasts. I remain your host, Kenny BADMUS. Until we meet again, thank you for being part of our program.
Your station, your heartbeat. Oxygen FM 96.